talk at QPL. And he's going to talk about how you can speedily contract ZX diagrams using triangles. Please, Mark.
Thank you, John. Let me, wait, I can turn my camera on. Okay, hi everyone. My name is Mark Koch. I'm going to talk about some work I did with my colleagues Richie and Hani on doing contraction of ZX diagrams with triangles and what kind of interesting things we can do with this. I would try to keep this short and sweet, so I probably won't need the full 1 hour time slot. So we should have plenty of time for questions. If any come up during the talk, just feel free to pop in and we can handle them. Okay, that being said, I think we can get started. So for this work, we're mainly interested in treating ZX diagrams as a kind of fancy notation for tensor networks that represent complex matrices. So we use the standard interpretation of ZX diagrams, where a diagram with n inputs and m outputs just corresponds to a 2 to the m by 2 to the n complex matrix. This means, in particular, if I have a diagram that doesn't have any inputs or outputs, then it just corresponds to a single complex number. And that's the reason why we typically call those diagrams scalar diagrams. And the main thing we're interested in is, given such a scalar diagram, compute this complex number. I call this contraction here, but you could also call it evaluation or something else. It's essentially just giving a scalar diagram, compute the scalar. As it turns out, this is a quite powerful operation, and you can do lots of interesting things with this. Arguably the most prominent application, and the one that has been studied the most in the past, is using this to do classical simulation of quantum circuits. So let's say we have some unitary U, and we want to compute some amplitude for some outcome x over input 0. Then we can just write down some ZX diagram. And the scalar value represented by this diagram is the amplitude. I guess we have to take the value and square it, and then we get the amplitude. But there are also other interesting things we can do with simulation that go beyond classical simulation of quantum circuits. In particular, if we move beyond the vanilla ZX calculus and look at some of the related calculi. One example we studied in our work is how to use contraction for ZXW diagrams to tackle a problem in quantum machine learning known as the barren plateau phenomenon. I will go into this more detail later. This diagram here might look a bit more intimidating than the one on the left-hand side, but yeah, we will go into more details later. Roughly, the idea is that a common thing you do in quantum machine learning when trying to train some parametrized circuit is you try to optimize some circuit parameters using gradient descent. And something you're very interested in if you try to do gradient descent is finding out how the gradient landscape of your circuit looks like. Because if you're in a very flat area of your gradient landscape, it's really hard to descend anywhere, and you're going to have a hard time optimizing it. And as it turns out, this diagram here, the number represented by this diagram, gives you a nice indication of how trainable a parameterized circuit is. So contracting this is quite useful. And then a third example I brought you here is that contracting diagrams can be very useful to solve certain counting problems. One example would be that you can solve counting set problems using ZH calculus. So given some Boolean formula phi, we can count the number of satisfying assignments to this formula by just contracting a ZH diagram. Okay. So all that is to say, being able to contract diagrams is very useful. You can do lots of interesting things with this, but it's also a hard problem, sharply hard to be precise, as evidenced by this application here. But now that I've convinced you, hopefully, that being able to contract diagrams is a useful thing to do, we can have a closer look at how you would actually do it. I'd argue there are two main avenues you could go down here. Either you can use some sort of tensor network-based method. For example, try to find some contraction path in the tensor network represented by a diagram and then contract it using tensor contraction, or some kind of state vector-based simulation approach. Or you can go with the stabilizer decomposition simulation strategy. And this is what we're doing in this work. This goes back to previous work by Bravi and Gossett in a 2016 paper who pioneered this approach. But this has also been already applied to the ZX calculus in a series of 2 papers by Alex John and also Renaud Bima in the second one. And this line of work resulted in the development of the QuiZX library, which is essentially like a fast Rust implementation of ZX calculus that is specifically designed to do these fast stabilizer simulations. And what we're doing in our work is we're building on top of QuiZX, so kind of adding new decomposition and simulation strategies to speed up simulation of certain circuits and also allow contraction of diagrams from other calculi. That's also the reason why when I show you some benchmarks later, we're mainly going to benchmark against QuiZX. So this is going to be our baseline. To give you a very rough overview of how the stabilizer decomposition approach works, it's based on the idea that Clifford diagrams, so diagrams where the phases are multiples of pi over 2, those are very easy to contract, which is a consequence of the Curtis-McNeil theorem. In the circuit world, you would do this using some stabilizer tableau method or something similar. In ZX, this is just, you can do pivoting and local complementations until the diagram is completely gone, right? So Cliffords are very easy to simulate. So the idea is if you get a circuit or some diagram that is non-Clifford, just decompose it into a linear combination of Cliffords and then contract each of them individually fast and then just add up the results. The catch is, of course, that the number of terms you get in this linear combination grows exponentially with the amount of non-Clifford stuff you have in your circuit or diagram. Okay, that was a very rough overview. To be a bit more precise, what people typically do, and what has also been done in QuiZX and previous ZX approaches, is that you restrict yourself to the Clifford+T gate set. The reason is that this makes it easier to decompose because you know more about the non-Clifford stuff that can be in your circuit in your diagram, because it can only be one kind of thing, namely T's. So if we have a Clifford+T diagram, we can write it in this form, namely a bunch of Clifford stuff at the bottom, and then some T spiders, which are just spiders with phase pi over 4 plugged in at the top. Right? So we can nicely separate the non-Clifford and the Clifford part into top and bottom. Then, for example, we can pick 6 of those spiders on top and decompose them using this equation here, which is inspired by 1 divided by Ravi, but then cast into ZX by Alex and John. And you can see here we have 6 T spiders. They're decomposed into a sum of 1, 2, 3, 4, 5, 6, 7 terms. Right? And notice that in each of these terms, the phases in the spiders are multiples of pi over 2, so it's all Clifford. So if we started out with T spiders at the top here, and we decompose 6 of them, we end up with 7 new diagrams that now have T minus 6 T's each. And then you just take each of these diagrams, and first you try to simplify them a bit. So you can take your favorite T count reduction technique or whatever and throw it at it with the hope that you might cancel out some T's, and then you just recurse. Right? So for each of those 7 diagrams, you pick 6 new T spiders, decompose them, then you get 7 squared diagrams. You do it again, 7 to the 3, and you essentially keep going until there are no more T spiders left, which means that all diagrams that are remaining are just Cliffords, and you can easily simulate them and then add up the results. Okay, so I think it's fairly easy to see that if you keep doing this, you will end up with 7 to the T over 6 terms overall. So the interesting thing here is that the runtime is exponential in the number of T gates that you had in your initial circuits. This is very different from state vector approaches or tensor network approaches, where the runtime is exponential in the number of qubits or in the amount of entanglement in your circuit. So here, this is very different behavior from other simulation methods. A typical thing people do is rebasing this exponent to be 2 to the power of alpha t, where alpha is about 0.468. And then the whole game is just trying to push this number alpha down. Right? So essentially, most research into the stabilizer decomposition approach is trying to find better decompositions that push this scaling factor alpha down to make things faster. And you can do this by, if we go back a bit, finding decompositions that are better than this one. So either also decomposing more T spiders into less terms or doing other clever things. The best alpha found so far is about 0.396, and this is where the current best stands. Right? But people try to push this down further, of course. Okay, I think that was enough background, so we can move on towards the things that we're trying to do differently here. To motivate this a bit, one of the restrictions of the existing approach is that you only work on Clifford+T diagrams. which means, for example, if you want to simulate a circuit that contains gates that are not T and not Clifford, for example, a toffee like seen here, you have to rebase it into the Clifford+T gate set, which introduces a bunch of T's. Right? For example, here you can see a standard decomposition of the toffee gate into 7 T's. And the same thing applies in the ZX setting. If you want to write down a toffee gate in vanilla ZX, you end up with something like this. So you get, again, 7 T spiders. And this is the decomposition that's used internally by QuiZX. And as you might imagine, this can be potentially catastrophic because the exponential runtime in contracting diagrams like this is exponential in the number of T's. So if you want to simulate a circuit that has lots of toffee gates, your T count might go through the roof really quick, and then it might become infeasible to simulate using approaches like QuiZX. So that's one of our motivations. We wanted to find a way to make it easier and faster to simulate circuits that contain many multi-control gates like toffees or other gates, but maybe even more controls. How are we going to do this? Is we're studying a certain configuration of the T gates shown here, which are denoted using this triangle node. And that's the interpretation. So this triangle node has been around for a while. We didn't invent it. It has a long history in the ZX universe. For example, it was very important to prove completeness. It has some interesting properties. For example, it maps the 0 state to the 0 state and the 1 state to the plus state. So it's quite funky, non-unitary, but it allows us to express very interesting things. I should also mention the triangle has an inverse, which you just get by composing it with 2 green spiders on both sides. The reason why we care about the triangle is that it allows us to write multi-control gates in a very nice way. So here you can see we just get this central spider here, and then triangles going out, and then a final inverse triangle here, which gives us a toffee gate with an arbitrary number of controls, which nicely generalizes. If we compare this to this thing here, this very much does not generalize. The typical thing you do if you want to construct multi-control toffee gates with more than 2 controls is you build kind of ladders of toffees, which can really get your T count through the roof. So this is really nice. It generalizes and is very compact. One thing I should mention here is that if all you want to do is have a nice representation of multi-control gates, you could also go with the ZH calculus, where you would get just an H node here that's connected. This would also be good. But the reason why we went with the triangle is that it also allows us to nicely embed the ZXW calculus into our diagrams, because we can represent the W spider from ZXW using kind of this configuration of triangles. And also the triangle itself can be useful, as we'll see later, and also plays an important role in ZXW and can be useful. So kind of our agenda here is, instead of writing toffee gates or W's and so on in terms of Clifford+T, write them using triangles, and then study how to decompose or how to apply stabilizer decomposition to diagrams with triangles instead of diagrams with T's. And then see if this potentially speeds up simulation of circuits or contraction of other diagrams that contain features from ZXW. Okay, that was a rough overview. We can go into a bit more detail now. A very typical thing you do if you try to work with ZX in software is that you turn your diagrams into graph-like form, where you only have green spiders and Hadamard edges. Because then the nice thing is you can just treat your diagram as an undirected simple graph. So we want to do something similar for triangles and add the notion of triangle edge, and then have a graph representation of diagrams that contain both Hadamards, but also triangles. But you might notice there's one small issue here. Namely, the triangle is a directed operation. So if you wanted to just add a triangle edge by itself, this would require us to represent diagrams as directed graphs, which would be kind of inconvenient. Therefore, we apply like a nice trick. Namely, we define the triangle edge like this, namely a triangle composed with a red pi node, because this is actually the same thing as the pi on the other side, so it's symmetric. Right? So using this trick, we can just keep the undirected setting and just compose pies, red pies, if we want to indicate a direction. One common thing people do as well is you can remove parallel Hadamard edges and also Hadamard self loops, which makes the whole definition well formed. And as it turns out, very similar rules hold also for triangle edges and also for the interaction between triangle and Hadamard edges. So for example, here you can see if we have two triangle edges, then one falls off. Or if we have a triangle and a Hadamard edge, then the Hadamard edge just falls off. And if we have a triangle self-loop, then the node just splits apart. So all this is to say, if we add triangles into the mix, it all still works out. We can still represent diagrams as undirected graphs, and yeah, it all just works, which is really quite nice. Okay, and so this is in terms of representation. How are we actually implementing this in software? Next, we can look at how we do the actual decomposition. The most naive baseline thing you could do is just reinsert the definition of the triangle node in terms of Clifford+T. Right? So we can write a single triangle edge via this diagram, which involves 4 T spiders. So if we started out with a diagram that contains T of those triangle edges, we would just turn it into a diagram that contains 4 times as many T spiders. Okay? And then we can just decompose it using QuiZX, using the existing approach. This would yield 2 to the beta T terms, where beta here is just 4 times the scaling coefficient we get in QuiZX, which comes out to be about 1.584. But if you start thinking a bit about this, you notice fairly soon that this is not optimal, clearly not, because if we just look at a single triangle, we can already decompose it into just 2 Clifford terms. So this would give us a scaling coefficient of beta equals 1. So if we have T triangles, we get 2 to the T terms overall, which is already way better than the 1.5 something we had using this approach here. However, as it turns out, we can do even better than this, because similar to how QuiZX can, or how QuiZX improves performance by contracting or by decomposing multiple T spiders at once into terms, we can also just decompose multiple triangle edges into terms and get a better scaling this way. The best decomposition we found looks like this. It decomposes 3 triangle edges into 5 terms, which gives us scaling of log 5/3, which comes out to be about 0.774. And this is the best decomposition we have that applies in the most general case, where we just have spiders at any location, we just have triangle edges at any location. But as it turns out, there are also some special cases where you can do better. We found these decompositions here that apply if our triangles are connected to a single Z spider with no other inputs and outputs. Because in this case, we can actually get away with only having 4 terms here, which gives us a scaling of 2/3, which is, again, better than the thing we had before. You might wonder why we don't have a case here where the angle is pi. We only have 0 and plus minus pi/2. The reason for this is if we have a pi spider with a triangle edge coming out, then this can all be simplified to something that's Clifford, but I will show you this later. Now, the very best case applies if we have multiple triangles that are connected to the same node, as shown here. Because in this case, instead of decomposing those triangle edges, we can just think about decomposing this one joint spider in the middle here. Because this only requires 2 terms, and luckily enough, it also cancels away the triangle edges we get here. So this means that if we have any number of triangles connected to a single Z spider, we can always decompose it into just 2 terms. Right? So this means if we have if we find one of those instances in a diagram with n triangles connected, then this would correspond to a beta scaling of 1/n, which is really good. In particular, as soon as n is greater than 1, so as soon as there are at least two triangles here, this is always better than any other decomposition we found. And also one nice thing is, if we're only interested in doing kind of this application for contraction of diagrams for a classical simulation, then this case always applies. Because in our representation of Toffoli gates, you can see this green spider here, which has multiple triangles connected, which also implies that no matter how many controls I have on my Toffoli gate, I can always decompose it into just 2 terms, right? Which corresponds to the fact that any Toffoli gate has a stabilizer rank of just 2, right? And this representation very easily gives us this for free. Okay, before I go here, I should mention that if you look at the second term above here, some of you might have noticed that this can be further simplified, right? There's this green spider with a Hadamard edge connected to this thing, so should just copy through. And in fact, the simplification is very useful. We have it here on a separate slide. The nice thing is that if I copy a spider through the spider here, then all other edges that are connected here fall off. In particular, all triangle edges that come out of here also go away, which is quite convenient because this could also further reduce the triangle count in my diagram. And this also works if we have a pi here. And in this case, we actually get this pattern here, which can again be copied through. So we get this nice cascading chain of simplification, which actually works really well in practice. What have we found? There are also some other simplifications that we did. This thing I mentioned before, if I have a green pi spider with an outgoing triangle, then I can just replace the triangle edge with a Hadamard edge. So this is always useful to do. And we also found this pattern here. So green pi spider with two triangles left and right, then I can just rewrite this into a diagram that only has a single triangle edge. We also looked at other patterns like these. Some of them are listed in our paper that contain many triangles, and then some of them are reduced into less. But practically, well, at least in running numbers, we didn't find that they were too beneficial. So in practice, we only use those two patterns here. Other patterns are more expensive to look for and don't occur too often. So we opted for just using those two to not incur the cost of looking for the more complicated ones because they didn't work too well. Okay, that was roughly how our approach works. Now I can show you some benchmarks. First, we started by running our approach on random 50-qubit Clifford+T plus CZZ circuits. Again, comparing our method against QuiZX. You can see QuiZX in blue and our implementation in orange here. And as you can see, at T counts around 50 to 60 in QuiZX, we already get like a 2 order of magnitude speed up compared to QuiZX. And while QuiZX reaches our timeout at around T count 60, we can easily go up to 100. And then we also did an exponential fit on those curves and get like a practical alpha or scaling coefficient, which in QuiZX would be 0.381, and we get 0.184. So about like better than like the slope is half of what we have in QuiZX. We didn't only run this on random circuits. We also looked at hidden shift circuits, which are a standard family of benchmarking circuits used in the stabilizer decomposition literature. There's one small thing to note here, namely that the hidden shift circuits, as initially proposed by Bravi et al., actually turned out to be very easy to simulate. This was done in QuiZX by doing some small tweaks to the optimization routine. It actually turns out that if you apply the standard ZX simplification to them, all T gates completely go away. So they maybe weren't the best benchmarking circuits. We tried to alleviate this a bit by changing the way the circuits are generated, namely using controlled swap gates instead of CZZ gates while constructing the circuits, which at least empirically makes it harder to simulate for QuiZX, as evidenced by this curve here. And again, you can see here the speed up over QuiZX for our method is even more drastic. For circuits that contain up to 10 C-swaps, we get 2 to maybe even 4 orders of magnitude improvement, depending on what instance we look at. And an important thing to note here again is we get a scaling of 2 to the 0.468 times number of controlled swaps, which is better than you would expect, because if we go back a bit, if we were just to use this decomposition here, you would think that if I have a diagram with X number of controlled gates, I would just use this decomposition, decompose each of them into 2 terms, and we get 2 to the X diagrams in total, right? But here we get 2 to the 0.5x, right? Which is an evidence of the fact that our simplification procedure greatly reduces the number of triangles we actually have to decompose, right? So this is evidence that our simplification strategy is actually quite powerful in this case here. To see how far we can push this, we also looked at circuits with 30 controlled swaps, which would be equivalent to a T count of 210 in QuiZX, and try to simulate them all and see how the distribution of runtime is. And as you can see, most of the circuits could be easily simulated in 10 to 20 minutes. There are some outliers that take a bit longer, but everything less than 1 hour. And I should also mention that this has all been run on a single core on a laptop CPU, right? So I think this is to show that using this decomposition and simplification strategy is highly effective compared to the Clifford+T decomposition used by QuiZX. Okay, this is all I wanted to say about doing classical simulation using contraction. Now I want to move on to this second application I teased at the very start, namely using contraction of diagrams with triangles to solve some problems in quantum machine learning, namely barren plateau detection. Roughly, the problem with barren plateaus is, or described by barren plateaus, is the fact that the gradient landscape of many parametrized circuits is exponentially flat. This is bad if you want to do something like gradient descent, because if your landscape is flat, you can't really descend anywhere, so you're stuck and it's hard to optimize. So people really want to find out which circuits have these problems, and for which circuits those problems aren't as bad, and which circuits are easier to train. On a more formal level, this can be characterized by the variance of the gradient of an expectation value. To see why this is the case, first we can note that for many circuits, the expected value for the gradient is actually 0, which I think makes quite a lot of sense, because if I start with a circuit and I randomly uniformly pick parameters, I would expect that the gradients also point in uniformly random directions, so the expectation will be 0. But now, if it's also the case that the variance of these gradients is 0, or is close to 0, this means that they're not only expected to be 0, but actually clustered close around 0, which means they tend to be very small, and yeah, which means we have small gradients, so things are very flat. So if we find out that for a circuit, this number is small, this is bad news and might be hard to train. So you might need to investigate some avenues to mitigate this. To give you an example, here I have a very basic ansätze with a bunch of parameterized RY rotation gates and then a bunch of CZ letters in the middle. And as you can see, here we plot the variance of the gradient for the very first parameter with increasing number of qubits. Notice that the y-axis is a log scale here. So with increasing number of qubits, we get an exponential decay in the variance, which is very bad. Right? So in this case, we would say that this ansätze here suffers from the barren plateau problem. Other ansätze, however, are a bit better. For example, this tree-shaped ansätze only gets a polynomial decay. Right? So in this case, you would say that we do not have this problem here. So people are really interested in figuring out which ansätze have this issue and which ones do not. And the very typical way you would compute these curves is either analytically, so you try to do some difficult math to figure out an exact formula for how the variance looks like with increasing number of qubits. And this can be quite tedious and is a lot of work. If you do this for a few circuits, this is already its own paper, essentially. So quite a lot of work. Or you just try to do it numerically. So you take your circuit, you sample some random parameter values, you simulate or run your circuit, compute gradients, do this like a few 100 times, and then you just have a distribution of gradients and you can compute some statistical variance. Okay? But as you can imagine, this is fairly expensive because you have to run the same circuit again and again and again to get an accurate estimate of the variance. And of course, it's also not exact, but just some statistical estimate of what the variance of your gradient would be. But as it turns out, we can actually use the ZX calculus to get an exact value for this. Because in previous work of ours, we showed that this variance number can actually be exactly represented using this scalar ZX diagram. It's not super important for the details here how this works. You can look in the paper here if you're interested in more. The main thing is that our friend, the triangle, shows up again here, which means that we can just take our existing software and throw this diagram at it and just contract it and get the number out. And the nice thing is this requires only contracting a single diagram versus trying to simulate the same circuit again and again and again using different parameter values. So this approach is way faster than this. We also tried some benchmarking on contracting diagrams of this shape. So we tried either using our method to contract this diagram versus using QuiZX and decomposing this triangle to Clifford+T. And again, we can see fairly massive speed ups compared to QuiZX. For some circuits, it's actually fairly comparable, but for others, for example, this circuit here, we get a 4 order of magnitude speed up for n layers here. So that's quite massive. Another thing we tried is trying to simulate or contract this diagram here using some tensor network methods. So not stabilizer decomposition, but just throw a tensor network contraction library at it and implement this diagram as a tensor network. Those are the extra lines you see now. We use the quimb Python library for contraction, using NumPy, JAX backends, and also using the Contangra optimizer in various combinations. And interestingly, you can see that in quite a lot of cases, we can actually beat tensor networks by quite a bit. Not in all cases. In circuit 2 layers down here, you can see that tensor networks scale a lot better than we do. But this is about to be expected. And as I told you, whereas for the stabilizer decomposition approach, the runtime depends on the number of non-Clifford things, so number of triangles in the diagram, whereas in the tensor network case, it depends on maybe the amount of entanglement or the amount of qubits you have in your circuit. So you can always find some cases one is better than the other, but nonetheless, I think it's very interesting to see that we can beat tensor networks in actually quite a few cases. Okay, so to summarize, we developed a technique to contract ZX diagrams that contain triangles to, number one, speed up simulation of circuits that contain many multi-corner gates, but also to contract diagrams from the ZXW calculus that contain triangles. We looked at the example to do barren detection, but there are also other interesting things you can do in ZXW or express in ZXW and then contract using our approach. In terms of future work, one of those avenues we'd like to explore is representing Hamiltonians in ZXW. Let's say you want to compute some expectation value for an Hamiltonian using this method. The classical thing you would try is just write this Hamiltonian as a sum of Pauli operators and then compute the expectation value for each of those Paulis and add them up. But we can actually express Hamiltonians in just a single diagram using ZXW. So it'd be interesting to figure out if this might be better than doing individual contractions, but just contracting the big thing at once. Maybe it is, maybe it's not. We have to see. Maybe we can also find better ways to decompose triangles. One thing that was very successful in the Clifford+T case is looking at partial decompositions. So ways to decompose triangles that might leave, ways to decompose T-spiders that might leave some T-spiders in there, but reduces the number overall. Might do the same thing for triangles, maybe if we can find something. And finally, it would be interesting to look into ways to do approximate contraction. Right? This might be particularly interesting for the ZX, for the case of barren detection, because there we're not really interested in what the exact numbers here are. We're more interested in the overall trend, right? Is the decay exponential or not exponential? So here we could actually tolerate quite big errors. So that's an interesting avenue to explore there. If you want to learn more about this, we have a paper on arXiv that you can check out, and I'd be happy to take any questions you might have. Thank you.
All right, thanks, Mark. So we have plenty of time for questions. So if anyone wants to go ahead, I see Sarah has raised her hand.
Thank you, Mark. Oh, I can hear myself. Okay, sorry. My camera is dead, so I'm just speaking through my mic. I have a question about the rewrite that you mentioned earlier about like the few steps. This might be a very basic question. So suppose you have a Clifford+T circuit. This means you have X spider and Z spider that have like different rotations. How would you push all the pi/4 rotations across like a Z-type pi/4 rotation across a spider that has, for example, pi/2 rotations, pi/4 rotation, etc.? Like, is this trivial?
Let's see, you mean, let me go back a bit. You mean, how do we get something like this where you only have T spiders on top? Yeah. So you can imagine you have your diagram where there are some T's and you can just unfuse them, right? And then you're left with the spider with no face, and then the spider with the pi/4 face just fuses out. So this would be the most trivial way to do it. And then if you have minus pi over 4, you could just have this with pi over 2 fused, which then becomes pi over 4. Does it make sense?
My question is, if you have, let's say, X spider that is of pi over 2, and then you have a Z spider that is pi over 4 on the right, and then you want to push the spider leftward across this X spider, can you do this just by unfuse the spider?
So if you want to push it, then you could push it through the X gate and then negate the phase. I guess this could work, but that's not what we have to do. Right? All we're interested in is kind of fusing it out conceptually to kind of get it away from the other stuff. So we don't push, we just try to unfuse it. But this is also more about thinking about how it could work. In practice, we just have the diagram. We don't unfuse anything. This is more about explaining how it works. They can just have pi over 4 spiders here.
And do you worry about putting the spiders in one layer, like this pi over 4 spiders, so that you can maximize or like you can minimize the number of T layers?
So we're not thinking about layering it. So yeah, I think one way people describe this in literature is that you might have in a circuit setting, you have a slice of Clifford stuff, then you have one slice of T gates, one slice of Clifford things. But that's not how we think about it, because we don't necessarily have a circuit. So we just have some diagram which does not need to be circuit shaped. So we don't even have to think about layers or anything. Right? It's just some graph with some pi over 4 phases in there. So we do not even need to think to layer it or try to arrange it anyway.
Okay, thank you.
All right, I see Alex has turned his camera on, so I think he wants to ask. Yeah, go ahead.
Thanks for the nice talk. Did you, so you have this rule that if you have a bunch of triangles adjacent to a single Z node, then you can decompose it in just 2 terms. This looks a lot like the 2-term decomposition of an H box. Is that really where this is coming from?
I'd say this is equivalent, yeah.
Is there a benefit to doing it one way or the other, or did you ever compare to like decomposing H boxes or anything like that?
So if we just talk about the multi-controlled gate stuff, so hopefully something, I think it should be 1-to-1 equivalent. You get the same thing out in the end, I believe. The main reason we went for triangles is because we started actually with this other application, so the machine learning application thing, and then we found out, oh hey, we can use the same thing also to do the TOEFL stuff. But yeah, you could also just start with ZH calculus and I believe get the same thing. You might want to think about some ways to simplify diagrams with ZH diagrams with H boxes in them, and there might be something you can get out of here, but we didn't think about it too much. But yeah, if we just talk about the single decomposition, I think it's 1-to-1 equivalent.
Okay. Yeah, that could be difficult thinking about simplifying with H boxes, because the automated things I know about tend to blow up the number of H boxes. So they keep the nodes the same or decrease the nodes or spiders, let's say, but make a whole lot of extra H boxes.
Yes.
Mark, I was wondering about your benchmark about the controlled swap sort of hidden shift circuits.
Okay.
So I think in the hidden shift circuit, there's just like this multiplied by 2, right? Where like they set them in the original benchmark, like, oh, we have like 10 CCZ, but actually it's 20 because like you have like 2 parts of the circuit that are sort of like orthogonal to each other. Is like this the C swap count, the actual C swap count, like the number of C swaps in the complete circuit?
Should be, I believe. I would have to double check in the source code, but let's see. I don't remember off the top of my head, but I would slightly lean towards it's the actual number, but I would have to double check. Here also it's pairs of C swaps, because you need to swap something, you need to swap it back later, so that the qubits aren't put in aren't permuted afterwards. Like we try to implement an oracle circuit here. So we don't want to switch things up too much. So they always come in pairs.
So like if you have 6 C swaps, there are 6 of them, but there's three different ones, and they're sort of paired up together. Okay, but like
Yes.
it's a 50 qubit circuit, but then you only have like at most 10 C swaps, which can only affect at most 30 qubits. So then 20 qubits sort of don't do anything then, right?
Yeah, there might still be like CZs and Z gates and so on, but yeah.
Have you tested out what if you have a difference in performance if you go to like say a 10 qubit circuit, a 20 qubit circuit, where like more of the qubits will be involved in the C swaps?
Yes, so I think I started testing with 100 qubit hidden shifts that were like very easy because it's super sparse. If you go down further, it probably gets even harder, would be my guess.
Yeah.
I didn't try too much. I guess the motivation was to choose something that you couldn't just easily do using state vector things.
Yeah, fair
But
enough. Yeah. Okay, thanks. Do we have any other questions from the audience? But I can ask one more. Like, are you gonna upstream this to the QuiZX repository?
If you're interested, I can put up a PR. Yeah.
Yeah, I mean, of course, of course, we're interested.
Okay. Yeah. Sure. Yeah, I have it on my local branch, but I can make a PR. I might need to clean up some things first, but
Yeah, nice.
yeah, I'm not sure. I guess yeah, it's adding like a new edge type. So if you're fine with having this around, yeah.
Right. Yeah, I think that will be fine.
I think it's okay.
And then so you also briefly mentioned W states, and I believe there's also papers by Arnie and maybe you as well, where the W states are involved in these calculations of these derivatives and stuff of things. Like, have you been using W states anywhere in these simulations?
So we're not using them in the benchmarks we ran here, because we don't really do sums too much. So in the differentiation paper, the triangle pops up if you try to differentiate, but it turns out if you do the variance calculation, they all go away again. So it doesn't pop up here. I think the next thing that would come to mind for me is in the Hamiltonian representation case, but it's a bit unclear if this works or not, because if I have a W state with n outputs, I can easily turn it or decompose it into n terms, but it would also have n triangles. So if I just do naive triangle decomposition, I would get 2 to the something n, which is, it would be probably worse than just a linear thing. So I think it would only be good if we could find some simplifications that apply. So maybe something in a circuit might cancel away some of the terms of the Hamiltonian, some vague things here, but yeah, I'm not sure.
Okay. Any more questions? Oh yeah, Sarah.
Yeah, I wish to follow up on the decomposition of multiply control NOT gate. So I wonder, have you compared your method with the one that proposed by Gidney's when he like basically decomposed the multiply control gate using Toffoli, Sina, and Scylla with like linear number of gate count? I'm curious to see if your method is comparable with this circuit-based method.
So this circuit-based method would decompose like a multi-control Toffoli gate into the normal 2-control Toffoli and bunch of C-nots, correct? Okay. I think our method probably still is significantly better because you would still need linear amount of Toffolis, would be my guess, right?
Yes.
Yeah. And then each Toffoli gives you 7 T's again. So you still get 7 times, so linear number of T gates for number of controls. So you still get lots of terms, whereas it's just 2 terms you get using our method.
Right. And in your method, do you need to use ancilla?
I'm not sure if you can cast it in terms of ancilla, because we just, let's see. We use this thing, which maybe you could call this thing an ancilla if you want to, but I'm not sure if you can. It's a bit hard to phrase it in terms of this ZX setting, because it's just not really a circuit thing that we apply here, right? We just have this diagram that represents this Toffoli gate. So I wouldn't necessarily call it an ancilla.
Then after the decomposition, is it easy to recover the circuit, or it's not a trivial task?
You mean after turning it into this form, or after applying the decomposition of triangles?
After applying the decomposition.
I don't see any good way to turn it back, especially after do some rewriting and the structure is lost. So yeah, I think if you'd only decompose, I think the thing you would get is identity minus some projector or something like this, which you could find. But I think as soon as you try to do some simplification and try to rewrite things, I think no chance.
I mean, also because you're calculating amplitude, right, which is a number, so it's not a unitary.
Oh, okay. Maybe I also missed the question. I'm not sure. You mean after the final contraction is done, after we get the number out, or after doing one single decomposition?
I was thinking about, so multiply controlled NOT gate is used a lot in quantum algorithms, and we wish to decompose them to a more elementary building blocks. And if I wish to use your method to perform decomposition, but then I still want to recover the circuit. So I just wonder, how can I use your method in constructing quantum algorithms?
Okay, I see what you mean.
The circuit back.
Yeah, I think that the term decomposing is overloaded here. So one is I want to represent my Toffoli gate in ZX calculus. So this is like one way to decompose a Toffoli gate, I guess. And this is something that can be reversible. So if I say I have some circuit in mind that I want to represent in ZX and do some reasoning about it, I could use this representation and then recover it back. But if we talk about, I want to compute an amplitude, so I want to do classical simulation, and I want to use stabilizer decompositions to simulate the circuit to compute a single number out, then you don't want to recover anything afterwards. So it's not really possible.
So I see what you're saying. Okay, thank you.
So if you want to do reasoning about circuits, you can use this representation, but that's not really what our method is about. It's more about how to contract, so how to compute the final number, the output at the end, and not really reason about the circuits themselves.
Okay, thank you.
I might want to add to that, Sarah, there is a different paper which you can maybe find later, where they also decompose these things into a sum of diagrams, but then each of the diagrams is a unitary itself. And then you can, in fact, decompose in a way where like complicated gates become simple gates, and you get an ensemble of circuits, and which, like, as a probabilistic mixture, approximates the unitary that you actually want. So that you can do stuff like this, but like the amount of samples you need to take is blows up exponentially in the number of times you do this method. So it doesn't really scale very well. But this is something you can do. Then you have to make sure that your decomposition into sums is also unitary.
Okay.
Right. Do we have some final questions? We're nearing the end of the hour.
I have a question.
All right.
Yeah, hi, Mark. Thanks for the talk. It was great. I was just thinking, looking at that decomposition of the W spider in terms of a triangle, whether you considered applying these methods to diagrammatic differentiation as well, whether that was useful.
I think okay. If we have the application in mind, we want to compute the gradient of a circuit or something, a parametrized circuit, at some particular parameter point, you could use this. But my feeling is that it would be easier to do like the normal parameter shift rule to compute gradients. My intuition would be this would be cheaper, because you would need a very big W thing here to make it work, right? Which means lots of triangles. I think you could apply it, but I'm not entirely sure how, if it would be better than using existing shift approaches. Maybe not. I'm not sure.
So you need a critical amount of triangles for it to be an efficient method, basically.
Yeah, the main thing is we've not experimented with trying to decompose those black W nodes, especially how. So my guess would be you would need some extra simplification things maybe to try to cut down the number of triangle or exponential terms you get. I could imagine that there might be something here, but we didn't run any numbers. But in principle, it could work. So you could use this to compute gradients, I think.
Cool, thanks.
And maybe related to that, have you looked at what the stabilizer rank of an n-arity W state is? Like if you, because you can write it as a combination of triangles, and then you have like these good decompositions for triangles. So does this give you like a good decomposition of a W?
So I think it's at least it's at most n, right? Because
yeah,
but I'm not aware of any other bounds. I don't know.
Well, there's like an n over 2 one, because you can sort of take them in pairs and you get
then you get you're right, yes.
You get the dot states.
Yep. I'm not sure. So I was thinking a lot about this for my master's thesis, because that's one of the things I worked on, the differentiation thing and trying to find gradient recipes by decomposing those guys here. I didn't find anything better, but who knows? Yeah.
Okay. All right. Any more questions? Okay, then let's thank the speaker again in whatever way you deem fit. You may clap in your living room. You may use the hand emoji from Zoom. But Mark, thank you very much.
Thank you.
So next week we will have another seminar, and we will have David Winderl, who will be talking about architecture-aware synthesis of Pauli polynomials. So we're very excited about that one. So I'll see you all again next week.
Bye.